the second derivative and curvature. We can use the second derivative to work out if a curve is completely concave or completely convex, or a combination of both. On this curve, I'm estimating the gradient here to be about 4, and then 2, 1, 0, then it becomes negative, minus 1, minus 2, minus 4. So I'm just estimating the value of the gradient at those points. So as x increases, we're moving in this direction along the curve, and you can see that the gradient continues to decrease. I can see this on a number line where my gradient here was 4, and then as x increases, if I just look at the gradient on the number line, so it was 4, then it went to 2, then it went to 1, and then 0, and then the gradient was minus 1, minus 2, minus 4. Anything moving towards the left is decreasing, so we have a decreasing gradient in the full range of this graph. So we can say this, and this is true, that d2y by dx squared, the second derivative, will have a negative value in this part of the graph. Or I can say the same thing in function notation. This is an example of a concave function, and this is the condition used to test if a curve is concave. You work out the second derivative, you make it less than 0, so you set up an inequality and you solve. And the solution to this inequality will be the set of values of x for which the curve or your function is showing concave behavior. A convex function. So if I estimate the gradient here, let's say the gradient there is about minus 4, minus 2, minus 1, 0, 1, 2, 4. As x increases, we're moving in this direction along the curve. Let's see what happens to the gradient. So the gradient's minus 4, and on a number line you're moving towards the right. Your numbers are increasing. The gradient continues to increase, and it continues to increase. So we're looking at a convex function. So as x increases, the gradient increases, and we can use the second derivative, so d2y by dx squared, make it greater than 0, so set up an inequality and solve, and it will give you the set of values of x for which the gradient is increasing and for which you have convex behavior. So the curvature here is convex. Example 1, we have a cubic curve, and looking at the coefficient for the cubic term, the shape will be something like this. So there's a section of the curve which is concave and a section which is convex. We need to find the set of values of x for the concave section and then for the convex section. So we start with the first derivative, second derivative. We need to solve for these conditions. So we have these inequalities based on the second derivative, 6x minus 12, less than 0, greater than 0. We solve. So for values of x less than 2, that section of the curve is concave, and for values of x greater than 2, that section of the curve is convex. So this is the graph, and as x increases, and we're moving along the graph in this direction, the gradient is decreasing. It continues to decrease. It's still decreasing until we hit x equals 2, this point. So this region was concave, and now the curvature changes from concave to convex, and x equals 2, that point there, this is a point of inflection. So the gradient was decreasing up to here, and now it starts to increase, and it continues to increase. So concave in this section and convex in this section. Example 2, we're looking for the point of inflection on this curve. So first derivative, second derivative, and at the point of inflection the second derivative is equal to 0, so we need to solve this as being equal to 0, which gives us x equals 2/3. Now the fact that d2y by dx squared is equal to 0 is not enough to show that at x equals 2/3 we have a point of inflection. So we can either now look at gradients on either side of x equals 2/3 and show that they both have the same sign, or we can continue with the second derivative and show that the second derivative changes sign on either side of x equals 2/3. So if we select a point on either side, so I've chosen 0 and 1, and substitute into the second derivative, we can see there's a sign change. That's evidence and proof that we have a point of inflection. So we can say x equals 2/3 is a point of inflection. It's where the curvature is changing for the curve. And because the coefficient of the cubic term is positive, the shape of the curve will be like this. So we have a concave section, and then at x equals 2/3, roughly here somewhere, the curvature changes from concave to convex, and that's your point of inflection. For practice, try these questions.